Hello again, and today we're going to talk about hypocycloids, high-speed travel between major cities. And the reason why we're going to talk about hypocycloids, high-speed travel between major cities, is because there's a special feature about hypocycloids that I want to introduce to you. This feature is a hidden feature, but I want to show you or demonstrate to you that this feature exists. So let's do that. Okay, hypocycloids between major cities. A previous video was my magic marble, and in that video I introduced you to the cycloid and the hypocycloid. The hypocycloid has a very special feature that I want to introduce to you in this video. That special feature is the orbital velocity around the Earth and the time required to orbit the Earth. Yes, the velocity to orbit around the Earth and the time required to orbit the Earth. Isn't that amazing how all of this mathematics is related? Well, that's the purpose of my doing these videos, to allow you to become acquainted and amazed with mathematics. And in so doing, maybe you'll decide engineering and mathematics is your career choice. Or maybe you're the next genius that will change the world of physics. Albert Einstein, as a little boy, would hang out in his dad's electrical company, and in so doing became infatuated with magnets and the compass. This infatuation led Albert to become a physicist and study light and time, which changed the world of science. It was because of Albert Einstein's equation, E equals mc squared, that we were able to build the atomic bomb. I also derived this equation in a video, Einstein's beautiful equation. So look for it on my Facebook page or on YouTube. So that's right. The hypocycloid gives the orbital velocity and the time required to orbit the Earth. Let's see how this is done. In my magic marble video, we talked about high-speed travel from New York to San Francisco, and we're going to do that again. In doing so, we use Isaac Newton's equation to determine the time and velocity required to travel between the cities on a hypocycloid. To arrive at a more accurate time and velocity required, we need the same type equation but with a slight deviation in construction of the equation. This derivation is quite difficult, so you won't find these derivations on the internet, and I'm not going to do them here. But if you want to know how to do them, send me an email and I'll send you the derivation, or I'll put them up in the video. It's a great deal of algebra, trigonometry, and a small part of calculus. Here, in this video, I'm just going to list the equations. But to calculate all of these derivations that you see me list here was about 18 pages or more. Okay. So, and it's a lot of algebra, and so I don't want to bore you with that. This is the equation Isaac Newton derived in 1697 to solve the brachistochrone problem given by Johann Bernoulli. Solutions of these type problems led to the development of the calculus of variations. The new velocity equation is derived via the gravitational potential energy inside the Earth rather than on the Earth's surface. I'm not going to show you how I did this. If you want it, send me an email and I'll put it up. I'll either send it to you or put it up in a video. But Isaac Newton's velocity equation comes from the energy equation. And so that's equal to V equals square root of 2g times h, height above the ground. The new velocity equation for a hypocycloid, once derived using the energy equation, you'll get V equals the gravity times the quantity, the radius of the Earth squared minus the radius to the bottom of the cycloid squared divided by the radius of the Earth. Okay, and we have also the length of the cycloid. The length of the cycloid is equal to 8 times a minus b times b divided by a sine squared theta a divided by 4b. You see how these get so confusing? And where b is the rolling circle radius and a equals the radius r is equal to the radius of the Earth. This is a very special equation, and I've derived this equation. You'll find this probably on the internet, but the special part is right here. This part, sine squared theta group, defines the cusp of the hypocycloid, and I'm going to show you what that is. So let's put all of this together. So the length of the hypocycloid, what we're going to do is we're going to go use to the first cusp. We're going to go to the first cusp. So how do we do that? Well, theta, the value of theta is greater than or equal to 0 or less than or equal to 2 pi b over a. Well, if I take 2 pi b over a and plug it in for theta here, I get what? 2 pi. Okay. And if I plug 2 pi b over a for theta, the b over a's cancel. 2 pi over 2, 2 goes into 4 2 times, and I get pi over 2. Well, a sine pi over 2 is equal to 1. So therefore, the hypocycloid is equal to 8 times the quantity a minus b, close quantity, parentheses, times b divided by a. Okay, let's put this together. So this is what the cusp is, okay, right there. And we only want 1. So we go to the first cusp. When a over b is equal to several different integers, you can get several different cusps. And I believe I showed that to you in one of my other videos where I had 4 cusps or 3 cusps. We did the Steelers logo, and I think it had 4 cusps each, you know. So there's different cusps, and this one is the one cusp that we want, okay? So from the center of the Earth to the bottom of the hypocycloid is the small r. From the center of the Earth to the surface of the Earth is the radius of the Earth. And from the center of the rolling circle to the outer part of the rolling circle is the radius of the rolling circle, and that's b. Here at A, we have our origin, and here at B, we have our destination. Okay? So that's what we're going to use, the first cusp. In each one of these hypocycloids you see me use here, you're only going to see one cusp. You're not going to see 3 or 4 or several. Okay. We will calculate high-speed hypocycloid travel to the following cities or locations: New York to Los Angeles, New York to San Francisco, London to Sidney, Australia, and from the North Pole to the South Pole. And the reason why I'm doing these different locations is to show you how this hypocycloid travel operates. And we're going to look at how deep they get and how they close in on a certain value the further away the two cities get. Okay, we're going to go from New York to Los Angeles. It's from New York to San Francisco first, then New York to Los Angeles, then London to Sydney, Australia, and then North Pole to the South Pole. Okay. And you know, London is up towards the top of the Earth, and Sydney, Australia is up down towards the bottom of the Earth. Although we are well aware that this type of travel is not possible due to several facts. The hypocycloid tunnels would have to be deep inside the Earth, which we will see. Longer distance tunnels will have to travel through the Earth's core, which is very hot and would melt your vehicle. So if we had a train of cars traveling on a hypocycloid, if they passed through the center of the Earth, I mean, we would melt the vehicle, so we couldn't do this. But there's interesting features about this that we want to look at, even though we know it's not possible to make this type of high-speed travel. Besides the extreme heat, the Coriolis effect, the Earth's rotation, would cause your vehicle to bounce off the sides of the tunnel at very high speeds, essentially destroying your vehicle. You see, as the Earth rotates, you're moving from east to west. So there's what's called a Coriolis effect. And if you drop down this hole, that Coriolis effect will cause you to bounce off the walls. For a tunnel going from North Pole to South Pole, you would drop down on the North Pole end and pop up on the South Pole end, if you could survive the hot core. But the problem with this is, when you drop in at the North Pole, you are traveling 1,040 miles per hour sideways due to Earth's rotation. So all of these issues make this travel impossible. But let's calculate the high-speed travel in the hypocycloid anyway to the following cities: New York to Los Angeles, New York to San Francisco, London to Sydney, Australia, North Pole to South Pole. The results of each one of the above calculations will move us closer to the result we are looking for: orbital velocity and the time to orbit the Earth. New York to Los Angeles travel. Okay. The distance from New York to Los Angeles on the surface of the Earth is approximately 2,458 miles. Let's first determine the distance from the Earth's center to the bottom of the hypocycloid. That's the equation I'm using. So the distance along the Earth's surface, S, is equal to 2 pi times B, and B is the rolling circle radius. So if we divide through by 2 pi, we get B is equal to 2,458 miles divided by 2 pi, which gives 391.2 miles. And so we round that off, multiply that by 2, and we get approximately 783 miles. Okay. R is the distance from the center to the bottom of the hypocycloid. So R is equal to the radius of the Earth minus 2B. So the radius of the Earth is 3,963 miles approximately. So we subtract 2B from that, and we get 3,180 miles for R. Okay. Now we do New York to San Francisco. And New York to San Francisco mileage is 2,568 miles. That's the distance along the Earth's surface. Okay. So we do the same thing. Divide 2,568 miles by 2 pi. We get B is equal to approximately 408. And we multiply that by 2. We get 817 miles for 2B. And we subtract 2B from the Earth's radius, and we get 3,146 miles. Then we do the same thing for London to Sydney's travel. Okay. And so we take 10,571 miles divided by 2 pi, gives 1682.42. We subtract, round that off to 1683. Multiply that by 2, we get 3,365. We subtract that from the radius, and we get R is equal to 598 miles from the center of the Earth to the bottom of the hypocycloid. Now, this is where it gets very interesting. This R is 598 miles from the center of the Earth. That's right through the core of the Earth. The core of the Earth is approximately, 760 miles radius. So we're going right through the core of the Earth. Okay, North Pole to South Pole. Well, the North Pole to South Pole distance along the surface is 12,451 miles. Okay, and we do the same thing. Divide that by 2 pi. We get 1981.6. Multiply that by 2, 3,963 miles. What? 2b is equal to the radius of the Earth. Well, if we subtract that from the radius of the Earth, we get r equals 0. And that's correct because there is no distance from the center of the Earth to the hypocycloid because we're drilling a tunnel directly through the center of the Earth. So there, r is equal to 0. If we plug in the variables calculated previously into these below equations, we'll get the velocity, the time, and the length of the hypocycloid. The velocity, here's our velocity equation. Here's our length of our hypocycloid, where b and r. And here's the time for a one-way trip in the tunnel, which is 2 pi b over r. That's one of the equations I'm using. Okay, times the square root of r times r minus b divided by the gravity divided by b. Here's a special feature about this time for the hypocycloid. When b is equal to r divided by 2, if you plug b equals r divided by 2 into the equation, that gives the one-way time, North Pole to South Pole, is equal to pi times the square root of r divided by g. That's from the top to the bottom. If you multiply that by 2 to return to the top, it gives the period, 2 pi times the square root of r divided by g. Okay. The time in terms of b, s, and r. Time for one-way travel in the tunnel using the rolling circle. Here's the equation. The time for one-way trip in the tunnel using the surface distance and the radius of the Earth this is the equation. The time for one-way travel in the tunnel using the distance from the center of the Earth to the bottom of the hypocycloid, this is the equation. So I calculated I derived all three of these equations. So if you decide you want to do this on your own and you looked up the surface distance between the cities, you can find what the time is. Or if you knew the distance from the center of the Earth to the bottom of the hypocycloid, you can use the third equation up here. Okay, so that's why I did that. Let's look at the table of values and animations. Enough with the equations. Okay, we have our New York to Los Angeles destination, our trip from New York to Los Angeles, and we're going to draw our hypocycloid. Okay, let's do that. Okay, our hypocycloid from New York to Los Angeles. Time for one-way travel is 25.15 minutes. The maximum velocity is 10,531.4 miles per hour. Our hypocycloid tunnel length, this underground, this red part here, is 2,811 miles. The radius from the center of the Earth to the bottom of the cycloid, here to here, is 3,184 miles, and the depth of the tunnel, 2B, is the depth of the rolling circle, which is 779 miles. Okay. And as you can remember from last time, I showed you my numbers over here changing as they were drawing the hypocycloid, but I'm not showing that now because I don't have the room for it on my screen and show you everything else. Okay. Let's look at the New York to San Francisco hypocycloid. Okay, we have our New York to San Francisco hypocycloid. Here's our New York to LA. So I've included the San Francisco trip. That's 25.69 minutes. The maximum velocity is 10,757.83 miles per hour. Hypocycloid tunnel length is 2,933 miles. The radius from the center of the Earth to the bottom of the hypocycloid is 3,145 miles. And the depth of the tunnel, the size of the rolling circle, is 818 miles. Okay, let's draw our hypocycloid. Isn't that amazing? Mathematics at work. Okay, let's look at the next hypocycloid, and that's the London to Australia trip. Okay, here's our London to Australia trip, and I've included the New York to LA and New York to San Francisco in this list up here, and London to Sydney, and also got the North Pole to South Pole, but don't worry about it, we haven't done that yet. So let's draw our hypocycloid. And as you can see, we're rolling our rolling circle around the inner side of the inside of the larger circle. And our London to Sydney, Australia time for one-way trip, 41.76 minutes. Maximum velocity, 17,482.41 miles. Hypocycloid total tunnel length, 7,746 miles. The radius R from the center of the Earth to the bottom of the hypocycloid is 598 miles. As you can see, we're passing through the core of the Earth. And the depth of the tunnel 2B, the depth of the rolling circle, is 3,365 miles. As you can see, the longer distance trips, you get closer to the core of the Earth. Okay, let's look at the North Pole to South Pole. Okay, here's our North Pole to South Pole. We have North Pole up here, South Pole down here. And what we have to do is we have to draw we have to input the correct equation so we can draw a hypocycloid from the top to the bottom, which is going to be a straight line. Okay. So, and I figured that out already, so you have nothing to worry about here. So here's our North Pole to South Pole. Let's draw our hypocycloid. Isn't that amazing? Okay. Our North Pole to South Pole time for one-way trip is 42.24 minutes. Maximum velocity is 17,684.92 miles per hour. Hypocycloid tunnel length is the diameter of the Earth, which is 7,926 miles. Radius from center of the Earth to the radius of the center of the Earth to the surface is 0 because we're passing through the center. And the depth of the tunnel 2B is equal to the radius of the Earth, 3,963 miles. And as you can see, our 2B rolling circle rotates around the center of the Earth. So the diameter is equal to the radius of the Earth. Isn't that amazing? So, and what happens here, if you were to drop into this, travel into this, let's say we were to be able to drill a hole through the center of the Earth, and you were to jump in or drive in or however you did that. The gravitational pull will pull you all the way down to the center, which then you'd be weightless at the center. And then you would continue on to the other end at the South Pole. Now, if you didn't grab onto anything or latch onto something, you would continue to oscillate back and forth from top to bottom. You know, so it would take you 42.24 minutes to get to the South Pole, and then you would go back up to the North Pole, which would take you 42 minutes. So therefore, That would be the orbit time to orbit the Earth is 84.48 minutes. That's the orbit time. Okay, let's look at some Excel sheets now. Okay, here's all our major city hypocycloid trips. I put this in Excel sheet. And so we have time for one-way trip, max velocity, all the way over to the depth of the tunnel. Okay. And the depth of the tunnel is really twice this, but I left it 2b so you can see that the radius of the rolling circle is equal to the radius of the Earth. But the depth of the tunnel turns out to be the same as the hypocycloid length, which is twice the radius of the circle. Okay. So let's look at diagrams here. We have our North Pole to South Pole. That's the one we're really interested in, because to travel from the top of the Earth to the bottom of the Earth in a tunnel, let's say we had drilled straight through the Earth, takes 42.24 minutes. But after you reach the South Pole, if you didn't get out, you would go back to the North Pole. It's just like going back and forth, up and down. So we would continue on. And so that would be twice that, which is the period, 84.48 minutes to orbit the Earth at that height of the Earth's radius. Okay. So the period is 84.48 minutes, which we get from our hypocycloid equations. The Earth is an oblate spheroid. So, and that's due to rotation. So it takes about 90 minutes to orbit the Earth at about 250 miles above the Earth. And that's about where the shuttle orbits. Okay. If we look at time for one-way travel, time t for our hypocycloid, here's the equation. Okay. But when a over b is equal to 2, and a is r, and we solve for b equals r over 2. If you plug b equals r over 2 into this equation, you get one-way trip time for north to south pole, which is pi times square root of r over g. And to go back up is the same thing, so that's 2 times that. So that's equal to 2 pi r divided by the square root, 2 pi times the square root of r divided by g, which is the same as the period here, right there. So the hypocycloid equation gives the period to circle the Earth, the time to circle the Earth, to orbit the Earth. Okay, the 3 time equations I gave in the presentation: time for one-way trip using the rolling circle radius, time for one-way trip using r from the center of the Earth to the bottom of the hypocycloid, and time for one-way trip in tunnel using the distance between the cities. I calculated all 3 of these for each one of our trips, and they came out the same. So that's what I want to show you about that. And the Earth's core. The Earth's core is the Earth's inner part, and is primarily a solid ball with a radius of about 1,220 kilometers or 760 miles. Okay, radius. So as you can see from our trip to London to Australia, we're well inside of the core. This is about 70% of the moon's radius. It is believed to consist of primarily iron, nickel alloy melted rock in approximately the same temperature as the surface of the Earth. So, as same temperature as the sun. So, as you can see, we could never use this type of travel passing near the core of the Earth. Okay. And that's about it for that. I'll include with this video on YouTube this link. In this link, you can get distances between any cities on Earth. And so if you decide you want to use those equations and do a few calculations on your own, you can get the distances between any cities at this link. Okay, well, that's about it for Hypocycloids high-speed travel between major cities. I hope you enjoyed this. I hope mathematics is one of the things you enjoy, and I hope you learned something. Until next time, thank you.